Here's a typical view of some well-worn lab sieves on the left. Most analyses are done in a sieve shaker, middle photo, and the results are given in one distribution of mass percent. Some reminders of the disadvantages of sieves. Unreliability. Worn sieves is probably the largest source of error in sieve analysis. Working sieve nests wear, resulting in reporting finer and finer distributions as time goes on. The sieve nest has to be recalibrated or replaced on a regular basis, but that's not done often in practice. And it's a time consumer. The sieve analysis requires anywhere from 15 to 30 minutes to complete, not including results calculation. Considerably longer than computer automated size analysis. And as with most characterization methods, sieves are one-dimensional in that they only measure one size parameter, the middle or width dimension of a particle. And operator error can easily occur in a number of operations. The particles remaining on each sieve must be carefully collected. Misweighing the sieve fraction is a common error, as are incorrect data entry and transcription, plus miscalculating the size distribution. Here's a superior alternative to sieves, Microtrac's patented Partan 3D image analyzer. This is a schematic which shows the simplicity of dynamic image analysis as used in the Partan 3D analyzer. The dry sample placed in the funnel above right moves on a vibratory feeder to the edge of the sensing zone, where it falls by gravity through the sensing zone and is collected in the sample box at the bottom. A strobe light on one side of the sensing zone lights the particles as the digital camera on the other side photographs the particles as they tumble through the sensing zone. A video file of the analysis is stored, and distributions and summary data for 36 morphological parameters for each particle are calculated and reported. And all this data is available as soon as the analysis ends, typically in under 3 minutes. This is an open instrument photo of the analyzer. The particles are seen tumbling through the sensing zone on the left, while the strobe and camera record the video file of the analysis. The video file can later be recalled and rerun under different measurement conditions or overlaid on a graph of a series of historical data. The sample analysis technology could hardly be more simple or more robust. This slide illustrates how the 3D mode works. The camera tracks the tumbling, rotating orientations of each particle, photo on left, and from those multiple individual images calculates the maximum and minimum parameters so that all 3 major axes are calculated. The advantages of the Partan 3D measurement over sieve analysis are numerous. The computerized automation eliminates the operator error. Automatic calibration gets around the error of worn, uncalibrated sieves. Partan analysis time is generally less than 3 minutes versus 15 to 30 for sieves, saving labor expense. The Partan also reports up to 36 different size, shape, and intensity parameters, user-selectable summary data, graphical and tabular distributions of each parameter, a scatter diagram display, and a viewable remeasurable image file versus one size parameter from Sibs. Also, every single particle in the sample is measured individually, and all 36 parameters for each are available in a selectable spreadsheet report, whereas Sieves make an ensemble measurement reporting a distribution of only one mass parameter. The Partan 3D analyzer is also the only image analyzer with a 3D mode, which reports the size of all three major axes, the length, the width, and the thickness, using a patented algorithm. This 3D mode also provides much more accurate morphological data than any 2D image analysis can. And the Partan measures each particle separately for infinite resolution. The three windows shown above are all contained in the Partan XY display window. The XY graph, upper left, is where up to 6 different size parameter distributions can be displayed. Here we're showing 3, the length, width, and area equivalent diameter as a volume % log distribution for a garnet sample. Also, up to 6 different historical records for one parameter can be overlaid here for comparison purposes. The windows shown under the graph is where the graph can be set up. The distribution type can be chosen, volume, count, or any shape parameter. Last, the general graph settings can be selected. In the upper right, the tabular distributions are shown, and below, up to 45 different pieces of summary data for all 6 parameters can be selected. Any of the 36 parameters can also be listed in the upper right table. This is the View Particles display window, where a lot of features are available to the user. The entire image file, as images or in data form, is viewable, sortable on any parameter, and exportable and printable. To point out use of the many features, follow the callouts with the red arrow, clockwise, starting with selected particle in the upper left. The particle in the blue box in the frame shot, upper left, has the values of all of its parameters displayed under data in the column in the upper right, in either the 2D or 3D mode. The numerical value of the sorted parameter can be turned on or off in the image file. Images can be sorted on any selected parameter. A query window for use in exploring the effect of different classifications of different components in the sample can be opened. An image data file can be exported as a spreadsheet. This display is extremely well suited for data interpretation, in setting up SOPs for data analysis and presentations, and especially for method development. This is the set of parameters Microtrac reports for its Partan dynamic image analysis product line. Now, rather than go into detail, I'll describe in 4 general terms what they measure. First, of course, is size. We give you 16 different size measurements of each particle in various diameters, lengths, widths, thicknesses, and more. The last 3 columns are shapes of various natures and are generally expressed as ratios of size parameters. Form factors include a number of different parameters that indicate how closely the particle is to being a perfect sphere, or various aspect ratios or elongations of the particle. Surface roughness parameters are just that. 3 different parameters can indicate the roughness factor of the particle surface. Other specialty parameters report the overall light intensity coming through the particle and the curvature of the particle as a gradient of light intensity. Just to let you relax a minute, don't be overwhelmed with all these choices. Only a few will be used depending on your application and the problems that you need to solve. And the Microtrac support team is always there to assist. Only one size is usually chosen, along with 1 or 2 form or surface roughness parameters. The many choices exist to provide the flexibility to optimize your particle characterization protocol. Now we'll go through 2 slides on particularly good applications for the Partan 3D. The first group listed here is all traditional sieve sizing applications where particles deviate significantly from sphericity. The 3 major categories are listed below: cylindrically shaped particles, spheroidal particles, and rectangular prisms. Sieves measure the middle dimension, width, which for cylinders is the diameter. The Partan measures all 3 dimensions, from which all the shape parameters can be calculated. The second category is spheroids, which can be looked at as systematically misshapen spheres. Just as a sphere is a rotated circle, spheroids are rotated ellipses. An oblate spheroid, flying saucer-shaped, is an ellipse rotated about its minor axis. Prolate spheroids, football-shaped, are ellipses rotated about their major axis. The third category of common non-spherical particles are rectangular prisms. Here the 3 major axes have 3 different dimensions, which are all measured and reported, and from which all the shape factors are calculated. And the volume of each particle is calculated by the Partan as the product of length, width, and thickness, which provides a much more accurate volume distribution than the equivalent spherical diameter as reported by 2D image analysis, and it provides overall more accurate size and shape data. The second category of applications for the Partan 3D are those traditional sieve sizing applications which are finding that they would also benefit from shape analysis. The granular fertilizer industry measures sphericity and surface roughness in addition to accurate size. Round, smooth granules within a small size range ensures a consistent leach rate into the soil, optimizing crop growth. Next, the frac sand application recognized the need for shape measurements as early as the 1960s, when Crumbian and Sloss developed their chart for using manual optical microscopy to quantify the sphericity and surface roughness of frac sands, or proppants as termed in the industry. With the Partan technology, a subjective, inaccurate manual microscopy measurement that took many hours to complete can be done in about 3 minutes. The frac sands have to be smooth and well-rounded to allow free flow of natural gas through the hydraulic fracture. Next, stone aggregates used in highway construction need to have aspect ratio controlled in a number of different size ranges to achieve proper packing, load-bearing strength, and wear resistance in the roadbed or airport runway. Sintered iron ore pellets need consistent size and sphericity for optimum packing and even melting in a blast furnace. Reflective glass beads used in highway coatings are optimized for performance when they have high circularity, transparency, and curvature, a shape parameter not measured by other image analyzers, as well as having consistent size. And finally, time-release capsules deliver their active drug ingredient at the proper consistent rate when they have the proper circularity and size. Here we show a few sample types that benefit from shape characterization: granulized fertilizer, aggregates, and proppants. And 3 more here of iron ore pellets, time-release drugs, and glass beads. This slide speaks to a feature in the Partan software which allows the user to develop the correlation of the Partan data to their historical Sieve data. Many users find this convenient to use as they transition from reporting the data in the Sieve analysis format to the Partan format. The graph shown is the final result of running this correlation feature in the software. The dark blue line is a Sieve size result, and the light blue curve is a Partan result run on the same sample. The orange curve is the correlated Partan measurement reported in sizes which would be reported as the Sieve analysis. This result can now be saved as an SOP file, and when that SOP is used for the Partan analysis, the size result will be reported as it would have been had it been run on the sieves used to develop the correlation. So the user can choose to report size data in the form which matches the way it was reported historically. Here's another correlation, as the last slide showed, but there's a much larger number of sieves that were used in the Sieve analysis, and there's a larger difference in the Sieve and Partan curves. But this shows that the correlation is every bit as good, even with a wider difference in the 2 original measurements. The correlated Partan data exactly overlays the original Sieve data to prove the robustness of the algorithm. And now, the big news feature from the Partan 3D is that with the 3D data, a new parameter was recently developed and proven which overlays Sieve data directly as well as correlated data does. Thus, for most practical purposes, eliminating the need to use the correlation routine. In the screen shown here, the Partan Sieve parameter data is shown plotted and overlaying the actual Sieve data. So only in a case of specific need or choice by the user would a correlation have to be performed by the user. The correlation routine remains in the software if desired. This slide shows the XY results graph with the Partan Sieve parameter plotted in dark blue, along with a dashed plot in light blue of the actual Sieve data, without running a correlation, verifying the effectiveness of this new parameter. Now I'll turn the presentation over to Dr. Phil Plants, introduced earlier, and he'll discuss the blending of Sieve or Sieve-correlated imaging data with laser diffraction. Phil?
Yes. Hi, everybody. What I'm about to describe to you is a method that will allow us to combine particle size data distribution over the range from about 60 nanometers up to 125 millimeters. So we're able to discuss the concept of nanoparticles as the smallest size all the way up to the largest size, which is actually being measured by the Partan 3D into sizes of inches. Just to start, and get some orientation, this is a image analysis measurement from the Partan 3D showing a measurement of very large particles. But at the same time, as you view the particle images in the top left, you'll notice that there are many, many fine particles mixed with the very large particles. Now, there are actually particles much smaller than that that the Partan 3D cannot measure. The Partan 3D is designed for fairly large particles, typically ranging from about 30 microns or 40 microns up to several inches. Now, on the next slide, what I'm going to show you is that using the concept of the sieve where the foray width is being used, what this shows is that based upon the callouts, it shows the data being correlated to sieves. There's a little tick box, and that indicates that the graph and all the data is undergoing a correlation. The graph shows a cumulative distribution as well as a differential distribution. The value that's being used for the sieve correlation is shown in the second callout at the bottom, and that is the F width that's being used for the sieve correlation. Now over to the right, you'll see several columns of data in the table, and that is data that has undergone the sieve correlation. I'm going to be using that data as a means to develop a entire distribution from very, very small sizes to very, very large sizes. Now, to do that, since the Partan 3D has limits on the bottom end, the Microtrac S3500 diffraction instrument has great capability all the way down to 10 to 20 nanometers. But the software that we're going to be talking about has been designed for sediments analysis, which takes us down to about 60 nanometers. Unfortunately, with the diffraction instruments, any diffraction instrument, there is a limitation on size for measurements. So we can't measure up to 125 millimeters. That might be desirable for sediments analysis or any other type of analysis where there is a tremendous distribution that's being involved. This screenshot is of Microtrac data that we are going to use to blend with the Partan 3D data. And you'll notice that the top size under these conditions of this measurement is about 1400 microns. If we go back to the Partan data, we'll notice that the size range there is down to about 60, 70 microns. So what we're going to do is blend these two distributions using Microtrac Flex software. So the solution for trying to deal with this situation is to blend the data. So on the next slide, what I'm showing is a screen from Microtrac Flex software where the diffraction instruments are being made. And this particular feature in the software allows blending of very, very large particles or even very, very small particles with existing other data. Now over on the left, one of the things I want to point out is the weight of fines. The very first thing that would have to be done is we have to separate these particles into two fractions and weigh them. And this is a very simple thing. It requires only one sieve to obtain the weight of the fines. The fines in this case are going to be the Microtrac diffraction data, since that's what's measuring on the finest end of the distribution. Now, some of these callouts, let me define. You'll notice that the size in the first callout on the left shows a minimum size of 0.5 microns, and that's based upon the data that we obtained from Microtrac software. So we're actually talking about submicron sizes here. The image data correlated to sieves has been attained by that correlation that Terry described and I showed you in the previous slide. All that was necessary was to take that information and enter those values manually. This takes on the order of maybe about 1 minute. You'll see that the bottom size on this is about 62 microns. So from this point on and going to the smaller sizes, we have to depend on the Microtrac diffraction instrument. Once that is done, those data are entered. The tabs at the bottom provide us with a couple of features. One is to perform the calculation, and this tab is shown as Calculate at the bottom. And then once that calculation occurs, which takes on the order of a couple of tenths of a second, then the next thing that happens is that all the data on the right side of the table is developed. And what we find is that we have the Microtrac diffraction data that's been extracted. The next column shows the data that's been blended, and this data is in terms of percent between sizes, which is very similar to Sieves and other computations and displays used in particle size measurement. And the last column shows the blended data as a cumulative distribution. Now, often it's desirable to present information in graphs because it provides such a visual impact. So another tab exists right next to the Calculate tab, and you can actually see that one slightly highlighted. This is called the graph, and once the graph is clicked, then the display at the right is shown, and this shows the blended data. And this is a typical distribution of sediments and, to use the term, dirt that's been found in various types of ice, ancient ice. So this is typical of what you would find with something like that type of material. So we now have the entire distribution from 30-some millimeters all the way down to 1/2 micron combined in one distribution. And now we have relative amounts, in this case in terms of volume, relative amounts of these various fractions along the size distribution spectrum. And with the next slide, please. In summary, sieving is an ancient size measurement. It actually dates back to Roman times when they were doing a lot of road building and things of that nature. They had to monitor size distributions. And we have reviewed the disadvantages compared to image analysis. The Microtrac's Part-An image analyzer provides many important and unique advantages with patented 3D software. The applications requiring image analysis include those which have other than spherical shapes, and those specifically which are already using them for that purpose. A new Sieve parameter is now available which utilizes the 3D data and can be reported automatically without going through a standard correlation routine to obtain it. It's a very simple feature to use and works very, very well. Sieve or Sieve correlated Part-An data can be easily blended with Microtrac diffraction data. As I pointed out, the data had been correlated from Sieve data, and it works very, very well to handle those situations where a very, very broad distribution is encountered.
Thank you for checking out this on-demand presentation. We hope you found the content helpful. We know transitioning from Sieves can be tough, but check out these comments from a customer who made the switch and is never looking back. Interested in seeing if a Microtrac is right for you? Please email Jason Noga at the address on the screen to arrange a complimentary sample analysis or schedule an on-site demo. For more information about our entire suite of particle characterization solutions, visit microtrac.com.